Okay, I think we probably should go ahead and start. This is Fred Aminzadeh, and I am pleased to introduce Kurt Strack, the President and CEO of KMS Technologies. And many of you probably know Kurt from his past work on with EMGS, and he used to be a chief geophysicist for Baker Atlas. He has many patents, and he has been focusing on fluid monitoring using electromagnetic techniques as well as AI. So his talk will be related to some of the work that he has been doing over the last several years. He also used to be chairman of the SEG Research Committee. So without further ado, I'm pleased to introduce to you Kurt Strack. Kurt?
Thank you, Fred, and thank you for the invitation. So I put a small presentation together to address this issue, and I like to emphasize some pitfalls and details. In particular, I noticed that there is a great interest in this, which for those of us that come from the logging area is quite surprising, because wells have been drilled since the 1990s remotely via the internet by every company, every logging company. But I think this is there is a time that this can be done effectively, but there are a lot of issues that people are not necessarily aware of and that we encounter. And I give you a little bit the story about it. Try to keep it simple. So those of you who are experts in it, you won't really see much new. First, I have picked fluid monitoring because Fred asked me for that, and that's mostly using electromagnetics, and I'll say a few words about electromagnetics. As I said before, internet-based systems are used in the oil industry since 25 years. They were all proprietary, and even today they are proprietary. They cost a lot of money, so it was very expensive. If you have a lot of money, you can do everything. The important part is to make it accessible and available. Today, we have all of the tools, and all of the tools are relatively inexpensive. We also know from the past decades that the best value of geophysical instrumentation with respect to reservoirs are permanent installed sensors. We also know that the service industry has great difficulties to adopt a new business model that they can actually embrace permanent installed sensors. So you can see that the largest companies had many times divisions going in and out, and because they just couldn't make money with it. The same with CO2. Today, of course, everybody is interested in CO2, but for the past 15 years, the big companies that had CO2 divisions tried to make money, and then they closed them again. What we are not considering in many cases is the human factor. So big companies are obviously paranoid about internet security, and so are several people. Today, people are more environmentally conscious, and the smartphone has changed everybody's life. So since we have the smartphone, everybody wants everything on the smartphone at low cost. So I was talking to one of my colleagues 15 years ago, and we both agreed, or he said, why can't I have all of this equipment on the smartphone? I said, I can make that for you easily, but the development costs money. But we still can't quite do it today. So I'll talk today a little bit more about those difficulties. We can put things on the smartphone easier today, but if you want to do it cost effective and make it available to everyone, that's a different story. in particular in the US, where we have some serious issues. And another country which is equally bad is Germany. Both countries have serious issues when it comes to telecommunication speed and cell phone speed and coverage, which is pretty much worse than in any country in Asia. They are much, much, much better. I can drive in any national forest in Asia and listen to my music out of the cloud. Try to do that in Texas. Or in Germany, 50 kilometers away from a big city. And we have, of course, a change in generation, which means we have the great crew change going on. We have to deal with the millennials and Generation X, and a lot of times they don't believe in experience, and they do everything based on their smartphone, and it's all in their smartphone, and that is the truth. So I'll talk a little bit about that. Let me just not go to read the slides. That's pretty boring. So let me just say one plug about our own effort. We started with this in 1999 and pretty much tried to put the first patent in place to start internet-enabled reservoir monitoring for hydrocarbon and geothermal, and develop from there the key strategy, which also included the sensors. Now, we have a large sensor family, and our systems are globally synchronized, so we can have a reference site in the United States and do an acquisition in Malaysia or someplace. We then had to develop a high-power transmitter because most reservoirs in the geothermal and oil industry are between 1.5 and 5 kilometers, and the same for CO2 injection sites. And then, of course, we had to harness 3D modeling code to a point where our 3D anisotropic code can be used quickly for and the practical discussions take longer than the scientific discussions. That's all I can tell you. Now, the pitfalls are very enlightening. So when we started in the early, 1999, we designed all sensors to be independent, fully digital, directly communicate to the internet. And we are not there yet, but we are not there yet because we didn't have the money. It's because there are just difficulties that takes time to get over. And our key objective is to make sure that what we do actually works in 23 countries for various applications. Magnetotelluric is a standard application, but that's used for geothermal and in some places for hydrocarbons. And we now recently have tied up with a seismic company that they can actually do the work. And that's pretty much, I think, the fastest learning curve we are going through, because they do things differently, and in most cases, they do things more correct than electromagnetic geophysicists. Now, just some definitions. There are some EM people on board, but I'll be talking about EM for electromagnetic, CSEM, which is controlled source EM, magnetotellurics. And we use a layer cloud definition for us internally because we distinguish between the data being inside and getting the data from all systems to the cloud is essential. And then you have your operations where you have the decision making, where you actually communicate back and forth with your instruments and you analyze operational parameters. And then you have the layer where you derive your images, which require deep learning and 3D modeling and a lot of scientific work in the background to feed your cloud engines or your computing engines in the cloud. And some of our colleagues are very proud that they still have a lot of clusters working to do this type of work, and it'd be cheaper than renting a Google Cloud space. Well, even though the electricity in our office is free, we turned the cluster off because it was too noisy and wasn't used enough, because the cloud is really taking over. For upstream, the key scenarios, the high-value problems are obviously geosteering in the reservoir for different applications, monitoring water coning, or this is also very important when you inject CO2 in reservoirs, and then also a type of imaging issues, and of course you can do this offshore and onshore equally well. For a long time we worked on offshore problems, and we then shifted our interest quickly for onshore equipment, and now everybody seems to be interested in onshore for the time being because of the renewable energy transition. So that's pretty much predominantly onshore, although there are already some quite big offshore projects coming online. So I expect that in 1 to 2 years we'll be looking at the same for offshore applications as well. And they've added the geothermal sketch here also. So these are the high value problems with the recording on the surface, in the water, and downhole. And the permanent sensors, they're grayish here, and I intentionally didn't highlight them more because they're not really part of this presentation. Then in a geothermal environment, you are doing it differently. You have essentially 1 or 2 geothermal wells feeding a power plant, and you want to not only monitor your geothermal reservoir. The reason why you have these big boxes there that my granddaughter plays with is because in urban areas, geothermal has caused many problems with subsidence, and so compliance monitoring or induced seismicity monitoring is mandatory. In a minute, I'll explain why I believe electromagnetics has a big role to play there. I think the cloud concept here is very simple for everybody that's interested in this, which I believe you all are. Now let's look at what electromagnetics or resistivity measurements are. This is an old SEG presentation. You have a rock pyrite, some mineral, and it is conductive, so there's a lot of current flowing, and sandstone is resistive. If you replace the rock with water and with sand, we have the same. Water is conductive, and oil or sand is resistive. I think that's something to remember. Now, if we look at a reservoir rock, and the standard model of a reservoir rock is that it consists out of grains. These are the mineral grains. In between is the pore space, and in the pore space are the fluids. There's some more detail to it, which we don't need, so I leave it with this plot. And a reservoir boundary is defined as the grain-to-grain contact between 2 different parts of the reservoir, which means in one case this is filled with one fluid, and this is filled with the other fluid. Depending on where you are in the reservoir, it could be either oil or water, but in most cases the water is below the oil. So this is the reservoir boundary. If a grain-to-grain contact breaks, it sends out a seismic signal. If it's large enough, it makes a microseismic signature. When you exercise any stress or strain on the matrix, you will also change the pore space in between the grains. And when you do this, you are essentially shaking the fluids. When you shake the fluids and it has any type of water saturation or component in it, the water molecules, since they are dipoles, will align and the electrodes jump from one to the other. So in all cases of enhanced oil recovery, the fluid resistivity drops tremendously because the fluid gets more mobile. This model doesn't only apply to hydrocarbon reservoirs, but it applies to any type of rock where you are dealing with normal pore space like this, and doesn't quite apply to fractured rock. That's secondary porosity. But where you have normal porosity, it applies. That also means that this could apply to earthquake prediction. And in many cases, this could explain better some earthquake precursors than the piezoelectric models that are being floated in the literature. And so you would get an EM signature. I'm in fact going as far as postulating that we get in more cases, maybe in 60 or 70%, even as high as 90% of the cases, an EM signature. And if you talk to some of my esteemed microseismic colleagues, they will tell you that the maximum percentage where they get a seismic or microseismic signature is 3 to 5% of the cases where actually microseismism occurs. So we also will get an EM signature earlier than a microseismic signature. And that is consistent with the work our Chinese colleagues have done to use electromagnetics for earthquake prediction. Here is an example where there was an earthquake in India, and by chance we were recording at that time in India, and these are then the signals on our 5 electromagnetic components, the electric and the magnetic fields, just to demonstrate to you that it's well known that this type of signals occur independently but at similar times. They do not necessarily occur at the same time. If they occur at the same time, you can use this as nuclear blast detector. Okay, we've talked about this. Just for those of you that are not familiar with electromagnetics, magnetotelluric signals are caused by sunspot activity. We have the sun here on the left. You have a solar flare. The solar flare sends solar wind against the Earth's magnetic field. The Earth is very little here. This bends around the magnetic field, which then makes a short, and in the magnetic fields you have induced current flow. And the closer these are to the Earth, going down to thunderstorm layers, which are of course of different nature, the higher the frequency. So that's the source. You measure this by measuring at the surface magnetic and electric field. And for magnetotellurics, you have to take the ratio of the magnetic and electric fields to cancel out the primary field, because you don't know where it is. And it's, of course, frequency dependent. So you take the ratio and you get an independent quantity for the different directions, x, y, and y, x. And if they're the same, the Earth is just layered. If they're different, it's two-dimensional, etc. For control source, you bring your own transmitter, and it is not this oil pump. The transmitter switch is actually behind this generator. No, the switch box is here, and the generator is there. And you inject the current. You do this to get a higher coupling to the subsurface resistivity and to overcome the electromagnetic noise. In urbanized areas, the noise is much, much bigger. We still have a lot of work to do to be able to measure almost anywhere near a city, but the systems are improving. And you have essentially a transmitter. You transmit in 2 directions, preferably. If you don't have 2 directions, you can just use one. And you put out a number of receivers. Here is a picture of one. You have a 3-dimensional anisotropic Earth. I emphasize that because I don't think people should interpret things anymore isotropic. You then try to make sense out of it. Obviously, if you have a Borel log, you try to calibrate against it. And from my experience, if you do that calibration process correctly, you will get very, very good survey results. Here is an example which kicked us off on the reservoir monitoring. This is from North Dakota, the Bakken. Some example, we got some logs from Microseismic Inc. around 2010, and I had a student calculate some 3D models. There's a transmitter here, and this is at 1,800 meters depth. We have a borehole receiver and a surface transmitter, and you can see that essentially the energy from that transmitter is being channeled into the reservoir. And you can measure it. If you translate these numbers, which are volts per meter, and multiply them with the transmitter and receiver moments, you would see that the response is in the millivolt range. It's very large, very unusual. And I was really surprised to see such a strong response, anomalous response at great depths, even though we were at that time long looking at reservoir monitoring. So subsequently, we tied up with a government research laboratory in Ukraine and formed a joint venture and are making sensors that go from DC to 200 kilohertz. Some of them we use for magnetotellurics, but others are used also on spacecrafts. They're flying on ESA spacecrafts. They're used in certain countries to monitor tunnels and offshore to monitor weapons floating above and all kinds of applications. This is, I believe, no, these are the marine sensors. These are the magnetotelluric sensors. They come in different sizes and flux gates as well. Then we made marine seismic NEM node, which we never really fully commercialized, but that went right along with the market in marine EM collapsing. And a borehole system, which we intend to use more frequently in land service for shallow boreholes up to 100 meters depth, so you can drill them very quickly. Now, one of our sensors are actually used by the Laser Interferometry Gravity Observatory that are trying to correct the influence of the magnetic field variations to the gravity wave. And you can imagine the gravity wave will also change the magnetic field. And obviously, the frequency will be in the same range as magnetotellurics. And somehow, that group likes our Lemma 120 sensor, which is the only one of the sensors that they really seem to like. Here we have the reference site they dug in. I found this on their website, and you can see they even have our name mentioned, which I didn't know until a few days ago. This is the data inside the laser interferometer ward, where they have two sensors mounted. You can find this on their website. And on the right side is at their reference site. Now, one of the problems we've had is easy to hook up a system to the internet, but it's not easy to transmit the data continuously for days without picking up noise in your magnetometers. Our magnetometers have to be very, very sensitive in order to be good. That means they will pick up any repetitive memory writing noise, for sure, cell phone transmission noise. We now have a client in Canada who managed to hook up the system through an internet connection, but there are other detailed plots with that part because the system is essentially not coming up fast enough. And so what we've done here on the left side, we have a noise-free solution where we're essentially taking a short hop jump outside of the box away from the sensors and the analog part, and then go into a buffer box where we buffer the data and go in that box to the internet. Here we have the wireless off or on, and you don't see any difference in the acquisition box, which we sometimes do when it's very cold and there's snow and ice around, and we put them in the same field container. But we'll try to make sure that the sensors and the analog parts are separated. You can see this noise, and I've talked with some of my colleagues at different companies, and I asked them, you surely can't stream all the data in real time to the internet. Yeah, we do. I said, what do you do when you're sending it to the cell phone? Well, we just turn on the acquisition and then turn it on afterwards. I thought that was funny. So you have to do it like that. So this is that box, and we do a very short, low noise Wi-Fi jump, and we do this with multiple other systems. We have many different MT systems in our system. All of this into the sensor itself, and the sensors are just too sensitive. And we are very happy that the calibration is very stable and they're very reliable. So it's very limited what we can actually put out of this acquisition box into here. So we took this out and go from there straight to the cloud. Here is an example of the different transmitters. Over the years, I've used different transmitters from 1 megawatt. I don't have a picture of the 1 megawatt transmitter, all the way down to 30 kilowatt. That's about the smallest one. But today, we are using essentially on routine basis this 150 kilowatt transmitter. And you just use a normal generator, any type of power function. Now, in the hardware, I mentioned it, the difficulty is the sensitivity of the magnetic sensors. In the manufacturing, the calibration must be extremely stable, and you need to be temperature reliable as well. Our own field crew 2 months ago was operating our system at -20 degrees, and they were complaining that the electrodes freeze up. And so I asked them if they put styrofoam into the box they had the acquisition unit. No. Well, they did a few days later, and so we were quite happy with that. So it's quite important. The other part is that the electric field needs to be very stable. There's a lot of problems with the electric field easily, but the stability of the electric field is really the secret in how you keep the electric field very stable. And I've seen a lot of surprises in that area. Marine and the borehole, you are more concerned about motion, pressure, and temperature, and you would use flux gate sensors because they're less motion sensitive than induction coils. And of course, for the transmitter, it's mostly a safety issue. I have an example where we used the cloud and put up a reference site 500 kilometers away from an MT survey, and essentially in real time derived the remote reference data. You see here the individual MT site. This is somewhere in the northern US. And you see here there is the sum, and you don't really know if this is noise or not, but once you apply the remote reference data, you can get rid of it, and you realize that you have some probably geologic channeling in this part of the profile. Now, how do we know this is correct? The red curve is a full 3D anisotropic model that we derived from the petrophysical analysis of well logs in the area. The total depth should be 3 kilometers. The logs go a little bit below 3 kilometers, yes. And the inversion results from the single side are displayed by the dashed line, and you can see there's mismatch here and there. This is only like 3 or 4 or 5 iterations, so it's not a perfect inversion. This is only quality assurance done overnight. And here you apply the log as starting model and run an inversion with the remote reference, and it just matches. And this is only a simple 1D inversion, not even anything more complicated. So immediately you can say the site's good, move on to the next one. You don't have to repeat this one. So that's a very, very important operating decision, because picking up a site costs money, and at -20 degrees C, it's not an easy process. Any 500 meters driving and transporting equipment takes a lot of time. Now, another part is the image focus. And I'll show you later more details between different parts, but we have a transmitter and a receiver, and in principle, we get information between transmitter and receiver. Here we have time domain displayed for 4 different sites. The sites are marked here from this transmitter. We are switching the current off and are essentially recording at these sites, and they will run in a loop. So they start at one time step, and then they go down with time, and you see that these are 2D sensitivities. You see that you get most of the information from underneath the receiver, but you get also information from underneath the transmitter. So we really don't know where the information comes from. And one of my younger colleagues asked me yesterday, well, where do you really plot this information? Does it come from here or there? I said, we really don't know. And you should have seen his face. He thought we know everything. And so in electromagnetics, a lot of people plot it halfway in between. And when you look at this, you say, well, it's probably the best place to put it underneath the receiver. Halfway in the middle is the worst place because there's less information coming from there. Well, I have news for you. I agree, but the best picture you get if you plot the information halfway in between. And I don't like it, but I have to acknowledge that that's the case. We don't really know yet why. So let's look at what we can do to improve that.
Chris, you have about half an hour if you want to allow time for Q&A.
I'm done. I'm almost done.
Good.
It's 2-3 slides and then just a summary. So what you have here is the frequency version, time domain version. So what you essentially do is do differential measurements between here, subtract this field in 3 dimensions from this field, and you are left with the information between those, and we call it OCM. And you see here for the frequency domain, when you model this, the current is flowing straight up for the frequency domain and also for the time domain. So we can improve the image focus for both methods. Here's the equipment for monitoring, where I have an example. We made a 195 channel system and took it to Asia. The client was afraid that somebody would add a system to it the next day, and they didn't want 3 systems, so they put a cage around the system. This, of course, messes up your web access. And I skipped the data. Let me just talk about 2 plots. We have changes with time after 2 days of fluid injection, and we get 30% variations from about 8,000 liters per hour fluid injection for 2 days. 30% anomaly, the signals are here. 200 meters away, the anomaly is only 2%. And here I would say it is noise, so we could clearly see it. And we also confirmed that with 3D modeling. In the interest of time, I appreciate Brad reminding me. So we see a similar level of anomaly for the faraway station. At the near station, we see a much larger anomaly, which I've also heard that other people experience also. Now, what do we do about the rest of it? Processing is obviously easy to put in the cloud. You have the data in the cloud. You need to provide the algorithms and run that in the cloud so that you can do that on your smartphone. And to do the interpretation, you would have to feed the artificial intelligence engine and train it to give you better results. And I'd say a few pitfalls about that. We found out when we applied this in the mid-1990s to logs and ran a lot of log inversions, 3D log inversions on 3 supercomputers, that 95% of our computing time was the forward model, not the inversion. And we stopped immediately using the neural networks for inversion and used them for forward models, which gave us instant results. And we were very happy with that, and we could significantly reduce our the time for our projects in the 3D modeling. The problem with inversion is that we have local minima and global minima. And if you do use artificial intelligence, in most cases you end up with the local minimum and not the global one. You need a good geologist to find the global one. And we were, in 9 out of 10 cases, failed in selling our perfect inversion results to the petrophysicists or geologists because they would always find another explanation. So the value lies in producing results in 24-hour cycle time. I think the technology is really not a big deal as long as it's reliable and you get these results. We feel that we've come a long way, that we can, we've reduced the cost. And if we can do it in 24 hours, we can apply it in areas where operating decisions are done. If the customer wants your work, you do the work, he gets the results the next day, and he reduces his cost, and he doesn't have to apply for a budget. It's a big advantage. This one I skip, and we see that the future is in very large channel count for seismic and DM together, and that in particular electromagnetics will be used in the EOR plus mode. The EOR plus means that you do enhanced oil recovery by reducing the carbon footprint, and you inject CO2 and get the carbon credits, plus you power this by renewables. It's being piloted in Norway, but the renewables are hydroelectric dams onshore, and they have to bring the power all the way offshore. And of course, this will allow you to get large real-time data volumes, which you need to use electromagnetics effectively. So I'm done.
Right. Thank you, Kurt.
Thank you, Fred.
We can open the floor for discussion and questions. Any questions? I actually have a question, Kurt. I understand that you have been doing some work with EERC, which is part of a SMART initiative. Would you care to say something about some of your carbon management work that you have done with them?
We are doing a base system. We've done part of DMT, and we are now doing 2 tests of the CSEM system before we take it to those pleasant temperatures in North Dakota. It looks like the diagram I skipped actually showed that you can see, I accidentally took out the formation there, but you can actually see the reservoir changes in the 3D model within a few percent. And so if we do the acquisition very careful, we should be in the green range. I'm very confident. So far, when we used careful 3D feasibility and survey design, we have always succeeded in the survey itself.
Okay. Yeah, since you have this PowerPoint up, when you say seismic/EM, you mean microseismic/EM, is that right?
Yeah, absolutely.
Okay. Well, any other questions?
When we use this in a hydrocarbon scenario for subsalt with ultra-long offset and want to do some tomographic interpretation of the seismic data, you can use the seismic data we require, but otherwise we are looking at microseismic.
Good. Any other question?
Valerie Smith here. So do you have much success in imaging CO2 plumes in the subsurface associated with CO2 storage projects?
Not yet. I'm sure you would know it if there is some a great and wonderful success. There are some success stories in Europe that the scientists that did the work say it's a success. Whether they convince it and it is a real success, that will take many years after you actually have the success. So, but it will obviously work. So I have no doubt that it will work. So I think you will soon see the success stories coming online as people do the work.
Thank you.
In the past, electromagnetics has been used for much more difficult problems than CO2 plume mapping. Mapping stacked reservoirs for oil-water contact is much more difficult problem. Time-lapse is usually easy because you subtract the 3D model from a 3D model, which is an easy one because most of the background 3D and the 3D noise doesn't vary. And so it's an easier problem. But at the same time, every time you take 1D model to subtract them, it becomes immediately 3D. So the trick in time-lapse is getting good data, and then it will in most cases work.
Okay, I know Roy has a question. Roy, can you just ask a question by unmuting yourself?
Okay, the question is this system approach being considered for monitoring Cascadia seismicity?
I don't know. I would have to look at the signal. The system can be used for any type of seismic sensor. So you can just put a different sensors in, because the land and marine systems have different input amplifiers. We could pretty much put any sensors into the system. So if you can monitor that type of seismicity from subduction zone, you can put some earthquake sensors on, like I just got half an hour ago, some advertisement from Greece. And sure, our marine sensor, our marine system are the same type of sensors they use. So you can put accelerometers, geophones, MEMS, whatever you want. It makes no difference. We control the amplifier, and the marine and land is different, and we will change it if necessary. So we can put any type of amplifier on it. It's not like we are stuck to anything.
Thank you. Yeah, no, I was just wondering, I was interested in, you were noting, you were getting unexpected depths for the signals, and I didn't know if that was deep, but monitoring the fluid and this whole idea of earthquake, there seems to be increased interest in the West Coast subduction zone. I know there's, ever since they wrote an article some time back about, we're overdue for a magnitude 9 there. I thought if there was interest in there, that we could get something developed not only for that, but for oil and gas. It seems like you described a crossover ground that would, if we could get the funding for it, that it would support both the environmental concerns and oil and gas. Just a thought.
That's 2,000% of my support. The system can easily do it with any type of sensor you need. I've been trying now for 6 or 7 years to get a consortium of universities together from Asia, Thailand, Indonesia, Malaysia, India, Germany, the US, to use this for volcano breakout and earthquake prediction. The money is there at the United Nations. I have failed to find one professor who takes the lead in writing the proposal. They are all interested, but nobody wants to lead. I found that very strange. So if we can find somebody to do this proposal, I will surely help as much as I can, because the system can easily do it. The case histories are there. Enough work has been done. The Chinese are exceptionally successful in earthquake prediction. And we focused on volcano breakout because of my relationship to Indonesia and other places in Asia. But earthquake, volcano, half a dozen one with 60 other. There is great interest in it. We have earthquake prediction systems, which are different systems based on changing of the ellipsoid of the magnetic field, that we've sold worldwide. They're being used everywhere. And they always ask us for interpretation software, but none of the academics that buy the system, whether that's in India or Mexico or Argentina or Brazil, ever make any software. So all what we say is you have to exchange it among yourselves. So it's well accepted that you can measure it. It's really an area where something needs to be done.
Kurt, I actually have another somewhat related question. Since you have a unique capability with your system to measure microseismic and EM in the same tool, have you thought about adding some sort of preferably machine learning based software to integrate EM and microseismic so that we can get the benefits of both and in order to either do CO2 management or oil and gas application, or perhaps geothermal?
Well, we are focusing on hardware manufacturing ourselves, so we don't do the research on the application side unless we are working with others. We are just finishing a system for KFUPM in Saudi Arabia and submitted with them last year 3 proposals where they would do exactly that. We would not be involved in that part because microseismic is pretty standard. But the integration is, of course, important. So, and I believe one of the proposals in Abu Dhabi has U.S. collaborator listed, Fred, but not on our side, on another project submitted by another group in Abu Dhabi.
I know about that.
So you should team up with that group that does the EM measurements, since your group doesn't have any EM measurements in it, and then do it together. Money comes from the same spot.
Yeah. All right. Any other questions? If there is no other question, I would like you to join me thanking Kurt for an excellent talk. All right. Well, thanks again, Kurt, and thanks everyone for joining this webinar.
Thanks to everybody, and thanks for listening, and be safe.
All right.
Thank you. Have a good day.
Thank you.